Neemt u al een plaats. Dames en heren, ik open hierbij de zitting en ik heet u van harte welkom op de hoofdcampus van de Open Universiteit hier in Heerlen. Ik heet u ook van harte welkom bij deze academische plechtigheid waarin mevrouw Alechina, benoemd tot hoogleraar Safe and Responsible AI, haar ambt zal aanvaarden met het uitspreken van een rede getiteld Can we make AI safe? Graag geef ik eerst het woord nu aan Natasha Alechina.
Meneer directeur Magnificus, geachte toehoorders, welkom bij mijn rede ter aanvaarding van het ambt van hoogleraar Safe and Responsible AI aan de Open Universiteit. Excuses voor het jaar. Oké, de rede is how can we make AI safe? And first, I obviously want to say, although we don't need this after the symposium we had this afternoon, why is AI safety a problem? Why do we have to worry about it? Artificial intelligence has made rapid advances in the last decade and is playing an increasingly important role in society. Most of the advances are due to development of deep learning and increasing availability of enormous amounts of data and computational power. So AI is doing very well. However, there is something stopping the adoption of machine learned techniques in many areas, especially safety critical areas, where it does matter whether things are safe or not. For example, completely autonomous robotic vehicles still have unacceptable accident rate. There's just recently another self-driving Tesla taxi has killed a pedestrian. Human pilots have not been replaced by self-flying planes. Human radiologists, in spite of what some Nobel Prize winners have predicted 5 years ago, have not been replaced by AI, although AI is obviously very useful in their work. Despite the impressive achievements and wide adoption, large language models such as ChatGPT occasionally make really basic mistakes. It's not surprising that they are programmed not to give advice on safety critical topics such as medical advice. They will just refuse to tell you anything if you say, what should I do for particular symptoms. So what do I mean by AI safety? It's AI system is safe if it doesn't harm people or other things in its environment in a way that was not intended by developers. So again, as Virginia said, I'm not talking about military applications. I'm talking about well-intentioned things like autonomous taxis and medical advisors and things like that, where you don't want any harm done to the users or environment. So first I'll give examples of what can go wrong in the safety, which everybody knows. So again, robots collide. This is a problem with the kind of standard AI system with collision detection, with route planning. And that was quite a big accident which caused a lot of harm to the environment and to the company, but fortunately not to people, unlike self-driving cars. I mentioned mistakes that LLMs make. This one is harmless and not safety critical, but just to give an example of when they just start inventing things. I asked about Moshe Vardi, and ChatGPT answered in particular that this well-known computer scientist was awarded Gödel Prize twice, which is false. And if you ask again or ask what the second one was for, then says, sorry, I didn't mean this, it was a mistake, I apologize for the confusion. We all saw this, I apologize for the confusion thing. And it's harmless if it is about just somebody's biography. The worst can happen is some loss of face if you introduce them at a conference. But if it's medical advice and it also starts inventing things, then obviously it's not safe. And that's an example of really unsafe use of ChatGPT. It's from the previous, 2 generations ago version. And somebody had a bright idea of using it to automate suicide counseling. And luckily it was never deployed, but being helpful, as they promised to be pleasant collocutioners and helpful, and trying to help people, it offered to help somebody to kill themselves. So that's about, first of all, would AI be suitable for this particular application question? And second, how do you align it with the values in a verifiable way so that it doesn't harm people even further instead of helping them? So first, I'll talk a little bit about safety of classical AI systems. That's a very well-established field of research, and mostly safety is ensured by formal verification, although obviously testing is very important as well. And formal verification establishes whether a given system, doesn't have to be an AI system, could be any computer system, satisfies a formal requirement. And that was my field of work for many years, formal verification of multi-agent systems. Multi-agent system is a system that is composed of multiple interacting agents. An agent is an autonomous AI system that has the ability to collect information, reason about it, perform actions in pursuit of either its goals or on behalf of the users. And examples of multi-agent systems are systems of controllers for satellites, could be seen as an agent, autonomous unmanned autonomous vehicles, smart manufacturing cells in factories, collections of factory robots on the assembly line, smart energy grids and nodes and sensor networks. And the systems are often very complex, and interaction between components and environment can lead to undesired behaviors, and these behaviors can be difficult to predict in advance. With the increasing use of autonomous agents in safety-critical systems, there is a growing need to verify that their behavior conforms to the desired system specification. And the classical example is avoid collisions in this kind of setting in delivery depot. Model checking is a key technique in verification of multi-agent systems. And it works by representing a system as a more abstract version, usually a state transition system, and specifying the property formally, property to check, and then we check whether the system satisfies this property. Like, it's not possible to end up in a deadlock, it's not possible to collide, it's not possible that the information leaks in a desired way, and so on. And temporal logic formula can say, in the case of the robots, the distance between robots is always greater than 0. One of the things that I and my colleagues worked are multi-agent systems with resources, where agents require resources in order to act. And in such systems, we consider actions that require time to complete, so time is a resource. You can achieve some goal if you have enough time and not if you don't. And they may also require other resources such as energy. In many applications, the availability or otherwise of resources is critical to the properties to be verified. But as usual, when there are numbers involved in analyzing a system. It is often an undecidable problem, and it's harder than the kind of straightforward analysis whether some state of the system can be reached. So in joint work with Niels Bulling, Stefan Demry, Brian Logan, Huang Nian Nguyen, Franco Raimondi, and Abdur Rakib, we worked on algorithms for verifying this kind of systems where agents need resources in order to act. And we have produced important breakthrough in this area by showing that even for systems where resources can be produced and produced in an unbounded way, we could still have decidable verification problem. So for some quite large class of expressive properties, it's still possible to verify the system, and this led to implementing tools for verification with resources. And that was a successful strand of work published in top AI conferences and journals, including International Conference on AI, Triple AI, European Conference on AI, and Artificial Intelligence Journal. Verification cannot solve all the problems, or sometimes it's not a very sensible way of going about first implementing something and then getting around to verifying it. So there is another related approach to producing provably correct systems, provably safe systems, and that's so-called formal synthesis. So you first specify what you want the system to do, and then you automatically synthesize a plan, say for a multi-agent system, that satisfies this property. So that was work at the University of Nottingham on synthesizing controllers for manufacturing robots. And that was a joint work with Giuseppe Di Giacomo, Paolo Felli, Brian Logan, and Moshe Vardi, and published in Triple AI conference. The last strand of work related to verification that I would like to talk about today is runtime verification. That is usually done when you want, maybe it's not possible to verify the entire system in advance because there are so many possible inputs to the system that you can't enumerate all of them. But at least you are trying to, as the system works, check that the behavior satisfies some properties, and if it stops satisfying it, then you issue a warning, or in some cases stop the system or do some kind of error remedy. So my current project is on warning a surgeon during robot-assisted surgery that something may be going wrong. So it could either be instruments not in the view of the camera, that the surgeon doesn't see what his surgical instruments are doing, or he's being or she's being too close to some anatomical structure, and so on, and can damage it, and so on. So that work is on verifying standard AI systems. And as I said, there's already a large body of work. And the important thing here is that there is a kind of manageable abstract representation of the system that you can work with, that you basically know how parts behave, and then you can check whether they satisfy a certain property. A system that learns, you don't have access to this clear structure. So I'll talk about particular kind of learning first, and that's reinforcement learning. And in reinforcement learning, in Dutch it would be learns by vallen and opstaan, by trial and error. So an agent learns to complete a task in a given environment. The agent doesn't know how the environment works, but agent can perform actions in the environment and observe the current state to choose an action and the resulting state to see the result. And the system responds with a reward, which could be positive or negative, or nothing. So the agent tries to learn a so-called policy, again, a way of which action or actions do I take in this state, that optimizes the rewards. And the rewards are discounted into the future, so if you can get rewards straight away, it's better than you procrastinate for a bit and then get the reward. So the optimal policy would be just achieving the goal as soon as possible. So the reinforcement learning agent looks like this. There is a learning agent and produces an action to the environment. The environment responds with a new state and the reward. And the agent usually keeps some kind of track of how the actions worked out. And the algorithm would be choosing which actions to try and how much variety to introduce and so on. So reinforcement learning is often used in robotics, where in this case a robot would be learning to walk. The actions would be what configuration of the joints, what kind of force to apply in different directions. So that would be actions, would be very many of them, obviously. And the reward you could give, for example, for not falling over, making another step forward. And then it would learn by falling over and then trying again. The challenges of reinforcement learning are that although it was, as I said, very successful in robotics and in other domains, it requires millions of training episodes before the agent learns to perform a complex task. So not very efficient, and it would be good to sort of speed it up. And from the safety point of view, reinforcement learning agents are essentially black boxes because the policy is so huge that you can't inspect it. And that makes it very difficult to verify that their behavior is safe. And an alternative to verification approach is to ensure, like with the factory robots, controllers, that we actually ensure from the beginning of the learning process that certain property would hold for the behavior of the agent. That it would learn how to move, but certain things it would never do in advance. To come back to the challenges is we try to direct the agent's learning with rewards, but rewards are always just an approximation of what we actually wanted to learn. And there are phenomena known as reward gaming, where the agents manage to get an optimal reward by doing some completely different thing from what you intended. It's very difficult to specify a perfect reward function. And a typical example of reward gaming is when, I'll give even a system later, but where the steps towards the goal are rewarded, so it never gets to the goal because it could just march on the spot, so to speak, and keep getting the reward. Another problem, which I also come back to later, is that during learning, the agent will try out all possible actions, including very unsafe ones. And it's all right in simulation that it can fall off the cliff a couple of million times and nobody is harmed. But if you have a very expensive robot with not very good physical simulation and you want it to learn in real reality, then you don't want it to fall off the cliff or try anything else complicated, dangerous. So, reward gaming. As I said, reward functions are only trying to hint at what you want it to do. And here is an example. It's a very simple environment. An agent is like a boat. The intended behavior that we want is that it races round and round and round some course. And the way to ensure it, there are 4 waypoints in this course. and we give a reward when it gets there. So you can imagine this also blown out a bit as a sort of larger course with only still 4 waypoints. So if you give a reward for crossing this tile, and nothing stops the agent just going like that. It doesn't have to go anywhere. It just stays on the spot and gets rewards. That's a typical reward gaming. And you could say, okay, we only reward it after it completed so many laps around the course. Like we wanted to do 100 laps, and we only give a reward once it does it. So first of all, the agent may not learn this way at all. It's so-called sparse reward, so nothing guides its search for suitable actions. The agent may still learn the wrong behavior, and it is very difficult to actually find out what behavior it learned. So, formal methods to the rescue, that's a big theme in my research. What we can do is we can try to constrain learning, like we did constrain the synthesis of plans, or that we checked that the system behaves correctly using verification. And it turns out that using this kind of in advance logic specifications for what we want of the agent is also making learning more efficient. But the main theme of today is that it also makes it safer. So here I need a little digression into temporal logic, and that's the language of specification that I'll be talking about. Linear time temporal logic describes properties of linear sequences of states, or paths, or traces. For example, those generated by a reinforcement learning agent executing its policy. In this language, you can talk about properties of states, also Boolean combinations of these properties. And we can talk about patterns on this trace. We have in the next state something happens, or in all states something happens, or something happens until something else happens. So here is a sketch. Here are 3 linear sequences of states. The first one says that in the next state some property A holds. Next one says A holds globally. And the last one says A holds until B becomes true. And it turns out that with just these 3 ways of specifying what happens at different parts of the trace, you can describe very important and useful properties, and at the same time it is reasonably efficient formalism to check that the properties hold. So some examples are don't give medication twice in a row. That, for example, some treatment says you shouldn't do this. You could say never on this trace will you find a pair of states such that in the first one medication is given and in the next one medication is given again. Stop when there is a human in front of you is, you could say, everywhere. If you see a human, then in the next state you are stationary. And don't bump into anything or don't break anything until you reach the destination can be expressed with until. So first of all, you have to reach a destination, and second, there is this invariant that you don't do some bad thing, unsafe thing as you're going. So this language allows us to both specify what we want, what kind of behavior we want to reward, and also what kind of things we want to prohibit. And I'll first talk about rewards. Reward machines is a mechanism proposed by some researchers in Canada, in Toronto, that can be used to specify much more explicit and declarative rewards. You just describe the behavior as a finite state automaton, the reward machine, or you can first describe it in logic and then translate it into an automaton. But they basically say your task consists of the following steps, and you get a reward only if you kind of reach the next step. And all the other things you are doing, you get nothing. If you do a bad thing, then you get a big negative reward. So here is an example of this object reward machine for the boat race, where we saw that the agent could cheat by just all the time encountering the same waypoint. So now we say if you start in the leftmost point here, you get a reward of 1 if you go right. Otherwise, whatever else you do, you don't get any reward. And then once you get this reward, you are sort of in a new state. And now the next reward you would only get if you encounter the sort of logically next one, waypoint. Not if you stay in the same place where you are. It doesn't help. So this helps with reward gaming. And it's a joint work that we are doing with Mehdi Dastani and Brian Logan and our PhD student Giovanni Variccioni, who couldn't come today, got sick. And it was published in European Conference on Multi-Agent Systems and in European Conference on AI just now. However clever the reward machines are, they can speed up learning. The agent kind of gets a bit extra information by looking at the state of the reward machine, what it should be doing now. So it needs fewer repetitions. However, you can't solve the problem of trying unsafe actions. It does get very big negative rewards for the unsafe actions, but it could still try them. So again, other people introduced so-called shields for reinforcement learning to stop the learning agent from even trying unsafe actions. It's something that sort of monitors agents' progress, I guess. No, it's not like runtime verification. It's something that the agent gets in advance together with the learning environment. And in every state of the learning environment, the agent gets a set of safe actions to choose from, because it's still trying to do some fine control, motor control thing, for example. So it still needs to try lots of things. You still need reinforcement learning, but it's stopped from falling off the cliff, basically. And shields are quite complicated things. You specify the property you want to hold, again in temporal logic. Then you synthesize abstract state machine, again to represent the environment. Then you define a so-called safety game, which is basically for each state, is it possible that I can have some safe action to stay in a safe region? Or would whatever I do eventually lead me to some bad thing, because you need to look ahead. Then you solve the safety game, and then you get a shield, and you give it to the agent. And the shield already kind of looked ahead, so in each state it can tell the agents what's unsafe, even if it looks perfectly fine, but maybe in 5 or 6 steps it's going to be in some really difficult situation. So we have a different approach, which in many cases is a lot more straightforward and also results in a sort of smaller learning space because the shield enlarges it quite a lot. And we do it action by action. For each action, we write when it is safe to take it. And that is again written as a temporal logic formula, only about the history of the agent. And unsafe actions are hidden from the agent, so-called masked. And this is joint work with Mehdi and Giuseppe De Giacomo and Brian Logan and Giuseppe Pirelli and Giovanni Variccioni. And it was published in AAAI in a special track on safe, robust, and responsible AI. So I'm very happy about this work. It is promising, but reinforcement learning is just one of the learning methods in AI. And the main big thing, which is obviously looming over everything, is generative AI and neural networks as well, but generative AI essentially is two neural networks. So future direction is obviously about trying to come up with similar safety guaranteeing approaches, but for generative AI. And I would like to combine the advantages of generative AI, which is very happy to produce solutions to difficult problems. The brilliant breakthrough was, for example, this faulting molecules, proposing how to do this. So it has great advantages. And learning in general is an extremely useful, unavoidable technique in many areas, like, for example, machine vision. You just can't do it without learning. But combine it with precise formal guarantees that are provided by formal symbolic approaches. And from the combination of these two different approaches, learning and formal methods, I hope a more robust, reliable, safe, and trustworthy AI would emerge. So how do we start on this? In fact, we already started with colleagues here at Open University. And a current project proposal is on generating personnel rosters using generative AI and verifying them using formal verification techniques. So it's a sort of generate and test kind of thing, where we solve a complex computational problem by asking generative AI to do it, but at the same time we verify that the result is actually usable. So, for example, that it conforms on all the sort of legal requirements, the reasonable hard constraints on the personnel roster, and also for softer properties such as fairness, which we have a great difficulty specifying formally, but need to talk to Arjen and get a better idea about that. So this is a joint EU project proposal with Jesse Heinig, Stefano, Gideon, and there are 14 consortium members from EU and Canada, and also with Matthew from Zuid-Holland. So that's just a kind of beginning that we could try this approach. We could also try other things. Maybe, again, we could somehow constrain learning. Maybe we could use safe reinforcement learning for doing the training of generative AI. So plans for the future are to build on my own work on combining learning and logic to create a strong research program on safe and responsible AI at Open University. Work together with AI group, as we heard in the symposium today. There is a lot of very relevant and very exciting research going on. So we can expand trustworthy AI research, and in the framework of the department's research strategy, collaborate with other colleagues in computer science on testing and security. That's very relevant topics for safe AI. And also pursue the multiple possibilities, some of which are already realized, for collaboration with colleagues from information science on trustworthy AI. So we already have a joint PhD project, and hopefully we can check that solutions there are reliable. And I obviously will continue to collaborate with colleagues in Utrecht and other universities in the Netherlands, and with colleagues in elsewhere in Europe, the UK, US, and China, on many other topics that I couldn't cover in this talk due to the time constraints and focus on just safe AI. And finally, I would like to thank the many people who made this work possible and who I worked with in the past and work now. And as I said, many people I haven't been able to mention in this talk because of the focus and limited time. So we did a great job with Jean-Jules Mayer on agent programming languages and verification of agents. Did much work with media on other topics as well. Worked with Hans on logics to do with information processing, and that's also actually relevant for safe AI because you can see how the agent's knowledge changes after communication. And many other people who, I don't know, hope that may be joining online. I would also like to thank my PhD supervisors who couldn't be here today. Michiel van Lambalchen, I hope, is listening online, and thank you, Michiel. It made a logician out of me, and it was a great time in Amsterdam learning logic and working with you. And Jon van Bentham, who is now in China, so probably is not listening, who also taught me logic and inspired me to take up this research even before I started the PhD. I would also like to thank my former and current PhD students, some of whom are here today. Thank you for coming. Some of them who couldn't come, but it's great fun to work together, and I'm looking forward to it. My colleagues at Open University and at Utrecht, thank you. Open University is a very welcoming place, and I thank the colleagues who organized this symposium today and everybody else I worked with already, and especially Bastian Heren and Petra for giving me this job and supporting me afterwards in this work. I already mentioned that I worked with many people. The DBLP online bibliography database lists 99 co-authors for me. And there's one person that I worked on 105 papers, which is Brian. So you could guess that I quite like working with Brian. I hope that we write a significant number of papers more. And it's sometimes difficult when we are still arguing about the complexity of some problem that it's time to cook dinner and we're still arguing about it. But it's very enjoyable all the time, all the same. I would also like to thank my friends and my parents for encouraging me in joining academia and always supporting me and having confidence in my ability to do it. And unfortunately, my father, who was my first academic mentor and taught me all the important things about doing research, has passed away and cannot be here. So I would like to dedicate him this speech to him. Thank you. Ik heb gezegd.
So we switch from English to Dutch again, and I know that you all can understand also Dutch. En we switchen van 2004 naar 2024 weer. U heeft er niks van gemerkt. Dat is een grapje. Goed, dames en heren. Waarde collega Alechina, beste Natasha. Proficiat met je benoeming en welkom bij de academische gemeenschap van de Open Universiteit. Ik ben zeer verheugd met je komst naar onze instelling. Dames en heren, professor Dr. Natasha Alechina solliciteerde in 2023 op de vacature voor hoogleraar Artificial Intelligence. En ze profileerde zich hier bij ons meteen al als een echte allrounder. Ze liet zich zien als iemand met sterke onderzoekskwaliteiten, bewezen leiderschapskwaliteiten en een hele duidelijke visie op AI in het onderwijs. Natasha is zeer gedreven om haar kennis over AI-technieken ook over te dragen op andere mensen, op een breder publiek en ook te informeren over de maatschappelijke en ethische consequenties van de AI. En dat past natuurlijk heel goed bij een open universiteit. En het blijft niet alleen bij woorden, want ze werkt ook dagelijks aan oplossingen, echte oplossingen, om AI veiliger te maken. En dat hebben we nu net ook gehoord in de oratie. En Natasha's maatschappelijke betrokkenheid die is niet nieuw. Natasha heeft al aan het begin van haar studie ervaren wat het regime in de Sovjet-Unie dacht over haar politieke opvattingen. Ze werd daarom het eerste jaar niet toegelaten tot de dagopleiding filosofie, alleen de avondopleiding. En filosofie moest ze toen doen met de energie die overbleef na een dag vrachtwagenvervoer in goede banen leiden op een bouwplaats. En in deze avonduren ontdekte ze haar liefde voor logica en bewijzen. En uiteindelijk studeerde Natasha cum laude af in de filosofie. Zij promoveerde, voor het eerst dus, in 1989 aan de Staatsuniversiteit van Moskou op een proefschrift getiteld Probabilistic Semantics and Inductive Logic. En in een tumultueuze politieke tijd in de Sovjet-Unie in 1991 belandde ze in Nederland bij het Institute for Logic, Language and Computation in Amsterdam, waar ze werd begeleid door professor Dr. Michiel van Lambalgen en haar promotor professor Dr. Johan van Benchem, die blijkbaar in China zit. Bij dit ILLC promoveerde zij in 1995 op het proefschrift Model Quantifiers. Haar promotor daar dus beschrijft haar als iemand met een scherp intellect, nuchter, want ze gelooft niet in de standaard illusies van deze wereld. En dat ze ook zeer plezierig is en heel loyaal in de omgang. Hij herinnert zich nog een hele mooie dag dat hij werd uitgenodigd bij Natasha thuis in Moskou. En natuurlijk naar Nederlands gewoonte een bloemetje had meegenomen. Het enige dat echter in de Sovjet-Unie te krijgen was, bleek en een verlept boeketje, dat tijdens de metrorit steeds verder verwelkte. En Natasha's reactie aan de voordeur was, oh wat aardig, Johan heeft gras voor me meegebracht. Hij wist toen ook meteen dat hij het heel goed met haar zou kunnen vinden. En dat soort humor toont ze ook bij de Open Universiteit en valt bij ons ook altijd heel erg goed. Natasha ging na haar promotie werken in Engeland, waar haar onderzoek verschoof van de wiskundelogica naar de computationele logica en AI. Natasha deed onderzoek naar agent systems, intelligente systemen die in staat zijn om in omgevingen zelfstandig acties uit te voeren en doelstellingen te bereiken. We hebben het net een beetje gehoord. En ze had bij de allereerste conferentie van de AAMAS, de International Joint Conference on Autonomous Agent and Multi-Agent Systems, in 2002 al een publicatie. En later is ze zelfs voorzitter geworden van die conferentie. En inmiddels is ze dus uitgegroeid tot een toonaangevend onderzoeker op dit gebied. In Engeland heeft ze dus ook haar partner Brian ontmoet. Naast dat ze echtgenoten zijn, zijn ze ook partners in de wetenschap. En ze hebben inmiddels meer dan 100 artikelen samengeschreven. In 2019 keerde zij terug naar Nederland bij de Universiteit van Utrecht, waar ook Brian als gast aan verbonden is. En haar echtgenoot beschrijft haar als een bijzonder mens en een echte doorzetter. En zo kennen wij haar ook. Zo werd zij na haar studie uitgenodigd voor een gastaanstelling bij Stanford University, maar werd een vertrek uit de Sovjet-Unie geweigerd door haar eigen universiteit. En in plaats van op te geven, richtte ze samen met haar vriendin en collega Dr. Vera Stebletsova, die inmiddels verbonden is aan de VU, gewoon een nieuw instituut op. Institute for Logic, Cognitive Science and Personal Development. En zo konden ze zichzelf een uitreisvisum verstrekken via hun eigen instituut. Als begeleider wordt Natasha getypeerd als een zeer zorgzame en ondersteunende mentor. Veel van haar promovendi zijn daarom ook in staat geweest om een onafhankelijke academische carrière op te bouwen. Haar voormalige promovendus Rustam Galoumulin beschrijft Natasha als de persoon die hem natuurlijk geleerd heeft toonaangevende logicus, hoe een toonaangevende logicus de moeilijkste wiskundige en computationele problemen benadert. Dat is een logisch, hè? Maar ook hoe je door de academische wereld kunt navigeren, dus langs decaan en rector, stel ik me zo voor, zonder concessies te doen aan de kwaliteit van onderzoek en begeleiding. En binnen onze eigen Open Universiteit is Natasha inmiddels ook een zeer gewaardeerde collega. Ze heeft haar stempel gedrukt op de onderzoeksstrategie van de faculteit Beta-wetenschappen en is lid van de facultaire onderzoekscommissie. In het onderwijs geeft ze inmiddels de volledig nieuwe cursus AI en maatschappij, samen met haar collega Clara Maathuis. En ook is ze voorzitter van de opleidingscommissie van Bachelor Informatica en Informatiekunde. En is zij afstudeercoördinator van de Master Artificial Intelligence. Natasha's brede, open en nuchtere blik op de wereld maakt het mogelijk voor haar om makkelijk verbindingen te leggen met hele andere vakgroepen, bijvoorbeeld met de collega's van het Trustworthy AI Lab, waar we eerder ook al iets over gehoord hebben. En op het persoonlijk vlak roemen haar collega's haar ook. Ze staat altijd voor je klaar en doet dit altijd met een glimlach. En die glimlach heb ik ook herkend in de 2 keer dat ik haar heb mogen spreken. En ik wens haar dus ook heel veel succes toe met haar leerstoel. En nogmaals, proficiat. Proficiat ook natuurlijk aan alle collega's van de Beta-faculteit onder leiding van de decaan, professor, dokter-ingenieur Petra de Weert-Nederhof. Wat een geweldige hoogleraar en collega hebben jullie er weer bij gekregen. En mijn felicitatie gaat natuurlijk ook uit aan je echtgenoot professor Dr. Brian Logan. Congratulations. En natuurlijk ook aan je moeder en andere familieleden die hier aanwezig zijn. Goed, dan wordt het tijd om het glas te gaan heffen op onze orator. En we komen ook bij de afsluiting van deze academische zitting. Ik wil u allen heel hartelijk danken en uitnodigen voor de receptie die op de benedenverdieping van dit gebouw zal gaan plaatsvinden. We gaan er zo gezamenlijk naartoe. Cortège voorop, voorgegaan door de pedel, die er zo wel zal aankomen. En als we daar dan zijn, dan stel ik voor om niet met z'n allen in de rij te gaan staan, maar u te verspreiden over de receptieruimte en zelf een goed moment te kiezen om de orator, Natasha, dus te feliciteren. Ik wil er ook op attenderen dat u kaartjes met erop de QR-code beneden ziet liggen. En daar kunt u ook de reden weer vinden van professor Dr. Natasha Alechina. Namens de Open Universiteitsgemeenschap dank ik u voor uw aanwezigheid en verklaar ik deze zitting voor gesloten. Dank u wel.